which process produces the minimum amount CO2 per kilogram of hydrogen? Steam reforming, partial oxidation, water electrolysis, or you don't know? Hydrogen is the most abundant element in the universe, which is found on our planet, mainly in water and organic compounds. Hydrogen can be produced from a wide range of resources using different feedstocks, pathways, and technologies, including fossil fuel and renewable sources. Currently, practically all industrial manufacture of hydrogen, globally about 85 million metric tons per year, is based on fossil fuels, mainly natural gas and coal, either directly using them as a feedstock and process fuel, or indirectly through the use of fossil fuel generated electricity. The main industrial sources of merchant hydrogen are the follows: steam methane reforming, about half of all hydrogen produced by steam methane reforming; partial oxidation and after thermal reforming; steam oxygen gasification of coal; refinery and chemical plants; water electrolysis; other minor sources like plasma pyrolysis; residual oil and biomass gasification. Also, water electrolysis and other electricity-driven hydrogen production process do not directly utilize fossil fuel as a chemical feedstock. One should take into consideration the global about 70% of electricity generation relies on combustion of fossil fuel. Take into account the predominance of fossil fuel in the power generation sector, it is evident that up to 98% of all industrial process of hydrogen relies on a fossil fuel, and particularly the oxidation transformation of fossil fuels with CO2 generation in final product of this transformation. Table summarizes the world average data on carbon dioxide emission in a kilogram of CO2 per kilogram of hydrogen product from the major industrial hydrogen manufacturing processes. The CO2 hydrogen yield values are arranged in two columns. Left one shows stoichiometry or theoretical CO2 hydrogen value based on the net chemical reaction, and the right column indicates the real-life process CO2 emission that include plant emission and those from electricity generation. Among all industrial hydrogen production technologies, steam methane reforming is by far the most important industrial process, amounting for more than 80% of hydrogen manufactured in the United States and 40% in the world. Steam methane reforming is also the cleanest among all processes. Due to the relatively high H2 to carbon ratio in methane molecule, it produced the least amount of CO2 emission per unit of hydrogen production compared to another technology. However, even this process produced close to 10 kg CO2 per kilogram of hydrogen product. After thermal reforming and partial oxidation are also fully developed mature technologies that are presently used commercially for hydrogen manufacturing. In particular, oxygen blown after thermal process is currently used in very large unit for the production of syngas for Fischer-Tropsch or methanol synthesis from natural gas. Feedstock with high carbon content compared to natural gas like naphtha, residual oil, coal yield significantly higher CO2 emissions, with the coal gasification process generating almost twice the amount of CO2 per unit of hydrogen product compared to steam methane reforming. The amount of CO2 produced by electrolytic processes is directly linked to the CO2 emitting capacity of power plants. The overall CO2 emission rate of the water electrolysis process is estimated at 24-28 kg of CO2 per kilogram of hydrogen. The steam reforming reaction was introduced to industry more than 80 years ago, although the reaction had not been subject to many scientific studies. Early work in the 19th century included reaction of hydrocarbons and steam over calcium oxide and nickel. Laboratory studies on the reforming reaction were published in 1920s, showing that product gas close to thermodynamic equilibrium were obtained over nickel catalyst. Fischer and Tropsch observed no significant difference when steam was replaced by carbon dioxide. It is surprising that Sabatier did not report any studies on steam reforming, as he studied numerous reactions on nickel catalyst. Among these was the methanation reaction, reported as early as 1902. The reforming process was adopted mainly in the United States, where natural gas was easily available as a feedstock, whereas reformers in Europe were initially reduced to operate on propane and LPG. The industrial breakthrough of the steam reforming technology came in 1962, where ICS succeeded in starting two tubular reformers operated at 15 bar and using naphtha as a feedstock. The first reformer designed by Topsøe was started in 1956 and the first naphtha reforming in 1965, followed by the hydrogen plant in 1966, which operate at 42 bar. The steam reforming process became the preferred technology for synthesis gas for methanol and other petrochemicals, oxo alcohols, citric acid, etc. The process in steam reforming technology has resulted in a less costly plant, in part because of better materials for reforming tubes, better control of carbon limits, and better catalyst and process concept with high feedstock flexibility. This process can be accompanied by a better understanding of reaction mechanism, the mechanism of carbon formation and sulfur poisoning, and the reason for the tube failure. Steam reforming of methane can be described by two main reversible reactions: the strongly endothermic steam reforming reaction and the moderate exothermic water-gas shift reaction. Methane steam reforming is highly endothermic process, so it is advanced at high temperature. The conversion in the endothermic steam reforming is increased with temperature, whereas the opposite in the case of the shift reaction. Methane conversion as a function of temperature in the combined methane reforming and shift reaction are shown in a slide. It is seen that conversion is strongly favored by high temperature, low pressure, and high steam to carbon ratio. From the thermodynamic viewpoint, steam reforming does not require high pressures. Generation of syngas is done, however, at high pressures, since downstream application of syngas in methanol and ammonia synthesis require high pressures. Also, application of high pressure is unfavorable for equilibrium and thus requires high temperature and excess of steam. Expensive compression of syngas is avoided. In practice, increase in temperature is limited by the thermal and mechanical stability of tubes. Other thermodynamic constraints are related to the risk of carbon formation when too little oxidant is present. The methane steam reforming reaction resulting in hydrogen to carbon monoxide ratio close to 3. Steam can be replaced by carbon dioxide, resulting in a ratio close to 1. The addition to oxygen in after thermal or partial oxidation reforming give a lower hydrogen to CO ratio. This ratio can be varied over the wide range as illustrated on a figure, as the reforming reaction are coupled to the shift reaction. In the manufacture of hydrogen, the reforming process is followed by water gas shift carried out in the presence of iron or copper catalyst at lower temperature to ensure complete conversion of carbon monoxide. Catalyst technologies are qualified as a complex system. Its complexity is not only limited to materials or composition and structure, but also includes simultaneously occurrence of mass transfer, heat transfer, and chemical reaction. The catalyst technology are often discussed or reviewed on the basis of a specific subject or piece by piece, while an actual working catalyst or catalyst process is an innovative integration of many technologies components, materials, chemistry, and chemical engineering. The figure shows a working catalyst bed reactor broken down in three different levels: macro level, reactor scale, micro level, particle scale, and nanoscale, active catalyst site or structure scale from atomic to nanometers. Clear catalyst research and development belong to a multidisciplinary field. Synthesis or preparation and characterization involve a great amount of material science and processing expertise, as well as solid-state chemistry knowledge. Reaction testing and application development comprise a core chemical engineering subject, hydrodynamic, mass and heat transfer, and chemical reaction engineering. Mechanistic understanding require reaction kinetics and surface chemistry. Methane is a stable and highly symmetric molecule. It's activated in a direct dissociative adsorption step, which is associated with substantial energy and entropy barrier. Various approaches have been applied to establish intrinsic kinetic or steam reforming of hydrocarbons. The first kinetic study of a steam reforming reaction will study the reaction on nickel foil in 1960s. Early work on the kinetic of steam reforming of methane was based on the assumption that the methane adsorption was rate determining. The work by Iglesia confirmed the first order kinetic with respect to methane, but with no impact on the rate of other reactants. This is in agreement with in general assumption of the first order depends of methane concentration. The work gives strong evidence that activation of methane is a rate determining step. Isotope exchange study on nickel supported catalyst at 600 degrees centigrade with CH4 and CD4 showed no formation of mixed isotopes, which would have been the case if the methane adsorption step was at equilibrium. Furthermore, Iglesia found no impact on the rate of another reactants. Similar results were observed on a number of group 8 metals. The overall reaction scheme present methane dissociatively adsorption, formation of surface carbon, adsorption of water, formation of adsorb oxygen species, and these oxygen species react with surface carbon and form carbon monoxide. The group of 8 elements are active for steam reforming, and typically nickel used as the catalyst, which has a reasonable high activity and a low price. To understand mechanism and kinetics of methane steam reforming, I recommend you to read a manuscript paper of Professor Iglesia in Journal of Catalysis, which is published 2004. The industrial catalyst is supposed to serve conditions in tubular reforming involving steam, partial pressure close to 30 bar, and temperature a reactor wall above 800 degrees. The support should be able to withstand these conditions without losing strength. Furthermore, it should not contain volatile components. Some of the support reactions are listed in table. High surface area support such as the gamma alumina can be used for catalyst for low temperature adiabatic reforming, but these support suffer from substantial sintering and weakening at temperature above 500 degrees. Because silica is volatile at high temperature in high pressure steam, it is now excluded from catalyst for steam reforming. Alkali used as a promoter to eliminate carbon formation may escape slowly from the catalyst. The alkali loss is enhanced by high temperature, but may not to some extent to be controlled by addition of acidic components. The volatile alkali may deposit in colder part of the plant where the resulting hydroxyl ions will be strongly promoter stress corrosion in stainless steel. Moreover, alkali may react with some catalyst support material such as alumina, forming the weak alumina, resulting in decreasing in the mechanical strength. While resistance to high temperature, catalysts based on magnesia are sensitive for steaming at low temperature because of the risk of hydration. The reaction may result in breakdown of the catalyst because it involves an expansion of the molecular volume. The equilibrium constant for the reaction is plotted in the right figure. It is seen that at the pressure typically of tubular reforming, hydration cannot take place at temperature above approximately 350 degrees C. Kinetic studies of the hydration reactions have shown that magnesia reacts via liquid phase reaction in which water condenses in the pores. Therefore, the rate depends on the relative humidity of the atmosphere, and in practice, hydration is a problem only when the magnesia-based catalyst is exposed to liquid water or is separated close to the condensation temperature. Hydration is eliminated for carriers where magnesia has reacted with alumina to form magnesia-alumina spinel. The spinel support is robust and can be withstand high operating temperatures. Typical reaction between nickel and support are listed in another table. At steaming condition, at high temperature, formation of the blue nickel aluminum spinel may start at temperature above 700 degrees C. A similar trend is observed for the reaction between nickel and magnesium oxide. Carbon formation cannot be tolerated as it may result in breakdown of the catalyst, increase in pressure drop and flow distribution, which leading to overheating of the tubes locally as a hotspot or totally as a hot tubes. This will limit the plant capacity or the life of the catalyst tube. Sulfur poisoning result in lower activity. The main reactions that lead to carbon formation are cracking and boudoir. Whisking carbon is formed as a characteristic fibers from carbon monoxide, methane or high hydrocarbons and may result in breakdown of the catalyst pellet. Broken catalyst and carbon may have a serious impact on the operation of the reformer. In situ high resolution transmission electron microscopy demonstrated that the process of carbon formation is very dynamic, involving drastic change in nickel crystal during the nucleation. It has also been possible to observe how the graphene layers grow from surface steps which are created during the nucleation and which moves as the graphene layers grow. This is illustrated on a figure. I'd like to note that the nickel particle size has an impact on the nucleation of carbon. The smaller the crystals, the more difficult the initiate of carbon formation. The rate of carbon formation was found to be far less on noble metals than on nickel. Group 8 elements are susceptible to sulfur poisoning, and sulfur must be removed from the feed stream. Natural gas may be cleaned over the active carbon, but normally all hydrocarbons feedstock are treated by hydrodesulfurization or over cobalt molybdenum or nickel molybdenum catalyst, followed by sulfur adsorption on a zinc oxide adsorption mass. Poisoning effects are often correlated with the poison concentration in the feed stream, which of course is an important parameter in practical operation. Under reforming condition, all sulfur compounds will be converted to hydrogen sulfide, which is chemisorphed on the metal surface. Nickel is the most sensitive metal. Sulfur has a strong impact on the reforming activity as a nickel catalyst, as we mentioned before, and deactivation is strong at small coverage of sulfur, and the catalyst is completely deactivated at full coverage. Hydrogen sulfide chemisorpts dissociatively on nickel. The chemisorption process is reversible, and in principle sulfur should be removed in hydrogen stream. However, the driving force are very small and decreases with decreased coverage. Sulfur may be removed by oxidation in steam. The exit gas shows the presence of sulfur dioxide as well as a hydrogen sulfide. The concentration at or inside the catalyst may not be equal to the concentration in the bulk of the fluid, and if the multiple fluids are present. The composition in one fluid must not be in equilibrium with the composition of in the other fluid. Mass transfer limitation play an important role on the rate of reaction and the rate of conversion and product formation. In heterogeneous catalytic reactions, however, the catalyst is usually in a different phase from the reactants. Commonly, the catalyst is in the solid phase, embedded in the reaction species, which usually are in the liquid or gaseous phase. Consequently, the reaction rate is principally relied on the mass transfer or diffusion between these phases. Since the reaction catalyzed by solid catalysts occur when the reactant molecules come in contact with the active sites, which are usually located inside the catalyst pores. In other words, the catalytic reaction is take place after the reactant molecules diffuse through the fluid layer surrounding the catalyst particles, then through the pore within the particle. The internal diffusion of the molecules competes with the reaction. At the same time, the external mass transfer is dependent on the stagnant film thickness and the activity of the outer layer. Hence, the diffusion of molecules is not only hindered by the other molecules, but also by the physical hindrances. The classical seventh step for the catalytic reaction involve diffusion of the reactant from the bulk phase to the external surface of the catalyst pellet, diffusion of the reactant from the pore mouth through the catalyst pore to the internal catalyst surface, to the point when the chemical transformation will occur, adsorption of reactants on the inert catalyst surface, reaction at specific active sites, desorption of the products, and diffusion of the products to the pore mouth, and the final diffusion of the product from the external pellet surface to the bulk fluid. The adsorption, surface reaction, and desorption are sequential steps. However, when a chemical reaction occurs on a surface, the rate of mass transfer to the reactive surface is in steady state and equal to the rate of reaction. If diffusion or mass transfer step are very fast, there is no resistance for the mass transfer from the bulk to the particle surface and from the particle surface to the active site in the pore. Nevertheless, the external mass transfer resistance strongly depends on the flow conditions, temperature, pressure, and superficial velocity in the reactor and the particle size of the catalyst. Varying this parameter can help to reduce the external mass transfer resistance. In case of the internal diffusion effect are significant and there is no external mass transfer resistance, then the concentration profile would vary across the catalyst pellet. In all reactor types, the desired conversion takes place on the catalyst. Side reactions, such as the carbon formation, are eliminated by use of the proper catalyst type, control catalyst bed inlet temperature, and a given steam to carbon ratio depend on the type of the feed. The role of the catalyst in all cases to achieve equilibrium conversion and maintaining low pressure drop. The space velocity has conventionally been used to determine the necessary catalyst volume for a given amount of feed, but this parameter gives no information about pressure drop, heat transfer, or risk of unwanted side reaction. So advanced models are necessary to evaluate design. The catalyst must also ensure equal distribution of flow between tubes and tubular reformer and across the catalyst bed in adiabatic reforming. Maldistribution may cause local overheating or channeling and hence a shorter lifetime of reactor. It means that the pressure drop should be carefully monitored during the catalyst loading. The catalyst should be mechanically stable under all process conditions as well as a condition during startup and shutdown of the reforming. In particular, resistance to conditions during upsets may become critical. Breakdown of catalyst pellets may cause a partial or total blockage of some tube resulting in hotspot, hot bands, or total hot tubes. The formation of carbon may result in the same problems. The shape of a catalyst pellet should be optimized to achieve maximum activity with minimum increases in pressure drop. The pressure drop depends strongly on a void fraction of the packed bed and decreases with increased particle size. Similarly, the effective catalyst activity per volume is proportional to the surface to volume ratio of the catalyst pellets due to the low catalyst effectiveness factor, typically below 0.1 for a tubular reformer. In order to fulfill the above mentioned requirements to the catalyst, the particles are usually made of ceramic material of cylindrical shape with one or more internal hole as seen in a figure below. The use of such catalyst formulation are often developed together with a new reactor concept taken at once in a higher effectiveness factor than achievable in conventional steam reforming. The tubular reformer. In the tubular reformer, the catalyst is placed in the number of high-low alloy reforming tubes placed in the furnace. The outer diameter of the tubes range typically from 100 to 200 millimeters and the tube length from 10 to 13 meters. Typical inlet temperature to the catalyst bed are 450–650 degrees C, and the product gas leaves the reformer at 700 till 950 C, depending on the application. The average heat flux from the burners may be larger than 150 kilowatts per square meter, and tubular reformer operate at a high mass velocity corresponding to Reynolds number larger than 5,000. Today, such reforming are built for a capacity up to 300,000 normal meter cube per hour of hydrogen or syngas. as the thermal efficiency of the tubular reforming and waste heat recovery section approach 95%. The remaining part is recovered from the flue gas. The heat is used for preheating of the reforming feed, combustion air, and for steam production. The combustion of natural gas with air is accompanied by formation of nitrogen oxide. As this becomes significant above 14–1500 degrees C, which is easily suppressed in normal diffusion flames. The problem is solved by use of low NOx burner, and further reduction can be obtained by cleaning the flue gas using selective catalytic reduction. As a critical issue in the methane steam reforming process, the limiting step is a heat transfer towards the reaction volume, since its high endothermicity requires high heat flux, and the catalyst has low thermal conductivity. Such a constraint imposes complex reaction geometry and very high temperature of heating medium, thus resulting in very expensive construction material, a very high reaction volume, and very low thermal transients. Therefore, it causes an increase of operation and fixed cost, and a reduction of the overall process efficiency. A flatter axial thermal profile through the catalyst bed can be achieved by using high thermal conductivity carrier, such as monoliths or firms, leading to heat redistribution along the catalyst bed with a consequent higher hydrocarbon conversion. In addition, the highly conductive support ensure a more uniform radial temperature profile, thus resulting in better heat transfer and a reduction of hot spot phenomena, and very stable performance. One of the main challenges in methane steam reformer is a tube life. The reforming tubes are exposed to high temperatures and pressure. Tubes are expensive and account for a major part of the total cost. The reliability of the tubes is important, since tube failure can result in long down period for retubing and hence loss of production. The mechanical tube design depends not only on the maximum metal temperature, but also on the maximum temperature gradient across the tube wall and the number of startup and shutdown. At high operation temperature, the tube metal creep under stress. The creep rate, which is almost constant over the time, increases almost linearly with applied stress and exponentially with temperature. The creep eventually results in rupture along the grain boundaries of the metal. This means that for a given tube, its life is very sensitive to small change in the maximum tube wall temperature. However, high catalytic activity is essential to ensure low tube wall temperature. A high catalytic activity can be utilized to absorb the same reaction heat at the lower temperature. Water gas shift. Hydrogen production from syngas by reforming or gasification require a shift of the gas composition toward the hydrogen and CO2 at the expense CO and water. This process step involves the hydrogen yield from the fuel conversion process and reduce the CO concentration in the product gas. The underlying reaction of this process step is called the water gas shift reaction. According to reaction enthalpy, the water gas shift reaction benefits from low reaction temperature. However, kinetic limitations are a critical issue. Hence, the process is conducted in two stages: adiabatic process with a high temperature shift stage and low temperature shift stage. The high temperature reaction is typically operated at temperature more than 350 degrees C, where fast reaction kinetics occur. This allows the use of small reactor volume. The high temperature, however, limits the reaction equilibrium, which result is CO content of approximately 3 volume percent at the reactor outlet. The low temperature water gas shift operate in the temperature range of 200-250 and favor an equilibrium toward hydrogen. A shift carbon monoxide outlet concentration of 0.1 volume percent can be obtained. The water gas shift reaction utilize fixed bed, typically with iron-based catalyst in a high temperature and copper-based catalyst in low temperature water gas shift reaction. Pressure swing adsorption. Pressure swing adsorption technology is based on a physical bonding of gas molecules to a solid adsorbent material. The adsorbent material can be a combination of active carbon, silica gel, carbon molecular sieves, and zeolite. The attractive forces between the gas molecules and the adsorbent materials depend on the gas composition, type of adsorbent material, the partial pressure of gas component, and the operating temperature. Highly volatile components with low polarity, such as hydrogen or helium, are essentially not adsorbed at all compared to molecules such as CO2, CO, nitrogen, and hydrocarbons. The relative attractive force of various gas molecules with typical adsorbent materials is shown in a figure. Light olefins are the feedstock employed in the production of vast array of chemicals, including polymers, oxygenates, and important chemicals intermediates. In a figure, the uses as well as the recent and predicted future growth of the olefin supply and chemicals are shown. Steam cracking and fluid catalytic cracking of naphtha, light, diesel, and other oil products are the most common method for obtaining this light olefin. In 2007, less than 3% of propylene was produced by on-purpose techniques, while fluid catalytic cracking and steam cracking account for the bulk of the propylene produced. A number of factors include the high energy demands of these processes, the low selectivity towards the production of olefin, decreased petroleum reserves, and rising oil price are driving the petrochemical industry to search for a more economic feedstock and more efficient conversion technologies. The development of an efficient and economic method of propylene production is therefore a great importance, I will say even more challenge. Over the last several years, considerable effort have been made to develop a new efficient methods for light olefin production, such as catalytic dehydrogenation. During the Second World War, catalytic dehydrogenation of butanes over a chromium-alumina catalyst was practiced for the production of butenes that were then dimerized to octanes and hydrogenated to octanes to yield high-octane aviation fuel. Dehydrogenation employs chromium-alumina catalyst and more recently platinum or modified platinum catalyst. Important aspect in dehydrogenation entail approaching equilibrium or near-equilibrium conversion while minimizing side reaction and coke formation. Commercial processes for the catalytic dehydrogenation of propane and butane attain per pass conversion in the range of 30–60%, while the catalytic dehydrogenation of high hydrocarbons C10, C14 paraffins typically operate at a conversion level around 10–20%. Let's consider commercial dehydrogenation technologies. And the first technology is a cataphin process. A cataphin installation generally consists 5 to 8 parallel adiabatic fixed bed reactors containing an chromia alumina catalyst. The reaction is run at temperature approximately 575 degrees C and pressure between 0.5 and 0.2 and 0.5 bar. Each reactor alternates between dehydrogenation, regeneration, a purge step, each lasting a few minutes, approximately 15–30 minutes between being needed for one full cycle. Each individual reactor is made to run continuously, so there are always some units performing dehydrogenation reaction, while other reactors are being regenerated or purged, which result in a constant flow of reaction products. A schematic of cataphin dehydrogenation installation is shown in a figure. The duration of the dehydrogenation stand depends on the heat content in the catalyst bed, which decrease rapidly due to the endothermic nature of reaction. Part of the heat required for the reaction is introduced to reactors by preheating the reaction feed. Additional heat being provided by adjacent reactors that are regenerating the cold catalyst. Moreover, the fuel gas is added to the reactor during the regeneration step to generate supplementary heat, and inert material is added to the catalyst bed to increase its heat storage capacity. As the catalyst remain in use for 2–3 years and progressively lost in activity with increasing time of stream by gradually increase in temperature to afford a constant dehydrogenation activity through the entire catalyst lifespan. Next process is Oleflex process. The Oleflex process by UOP uses a very different reactor design comprising fluidized bed reactor, a catalyst regeneration unit, and a product recovery section. A schematic representation is shown in a figure. The reaction is run using a platinum tin catalyst at pressure between 1 and 3 bar and temperature ranging from 525 to 700 degrees. 3 or 4 adiabatic radial flow reactors containing the catalyst are connected to series with preheaters in between. These gas flow preheaters represent the main source of heat of the reactor system. As the catalyst flow through the system is last reactor being connected to continuous catalyst regeneration unit that then regenerates the catalyst by burning off any carbon deposit and redisperse the platinum on the support materials by means of treating the catalyst with a chlorine air mixture. The entire system is designed to operate continuously. The regenerated catalyst is then reintroduced to the first reactor, completing entire cycles every 5–10 days. Product recovery is done by cooling, compressing, and drying the reactor effluent, hydrogen being cryogenically separate from the hydrocarbons. Another process, the steam active reforming start process. The start process utilizes a very different reactor setup. The reaction is run at 69 bar and a temperature between 500 till 600 degrees C. Steam being added to the feed to reduce paraffin partial pressure and coke formation. Because the catalyst has to be stable in the presence of steam, platinum tin supported on zinc alumina is used with calcium magnesium aluminate as a binder. Very little coke is deposited on the catalyst surface, and those dehydrogenation cycles may be as long as 7 hours before regeneration become necessary. A fixed bed reactor system is used, consisting of two separate reactors placed in series. The first is a top-fire tubular reformer type reactor, which is externally heated by an oven. Most of the heat is provided at the top of the reactor, where the dehydrogenation activity is the highest. The gas mixture exiting the first reactor is cooled prior to be introduced into the second, so-called oxy-reactor, where oxygen steam mixture is used to selective combustion or part of hydrogen and shifting equilibrium towards a high olefin yield. In addition to the combustion of the hydrogen provides the heat required for the additional conversion of propane. The olefins in the resulting gas mixture are separated from any residual hydrogen and other side product, which are combusted to heat which necessary to dehydrogenation reactor oven. Next process is PDH process. The Linde BASF PDH process, of which a schematic representation shown in a figure, used as well platinum tin catalyst but supported on zirconia oxide for dehydrogenation of light olefin isothermally at temperature 590 degrees. The process shows very similarity with the start process, as a reaction feed is diluted with steam and an external heater fixed bed reactor is used. 3 of those reactors operate in parallel, which 2 in dehydrogenation and 1 in regeneration mode, ensuring a continuous flow of reaction products. A mixture of air and steam is used to regenerate the catalyst, and the reactor is purged before and after regeneration step. Let's consider thermodynamics of the process. From the chemical perspective, dehydrogenation is a one-step reaction through which light paraffin can be converted into the corresponding olefin and hydrogen. The reaction is thermodynamically limited and highly endothermic, which according to Le Chatelier principle imply that higher reaction temperature and lower paraffin partial pressure are needed to achieve high conversion. Indeed, a temperature of 550–750 are typically required in dehydrogenation of C2, C4 paraffins to obtain alkane conversion more than 50% at 1 bar. Moreover, given that the enthalpy required to dehydrogenation alkane decrease as the chain become longer, consider a large amount of energy is required to dehydrogenate light paraffin on a maize base. The pressure dependent is also shown on a figure. Lower pressure clearly resulting at high olefin yield at a given temperature. The CH bond in paraffins and olefins are considerably more reactive than CC bond, meaning that catalysts that favor CH bond over CC bond cleavage are required to avoid side reaction. An additional complicated factor is that olefins are considerably more reactive than the paraffin, which can be further lead to unwanted side and secondary reaction. The CH bond in paraffin and olefin are considerably more reactive than CC bond, meaning that catalysts that favor for CH bond over CC bond cleavage are required to avoid side reaction. An additional complicating factor is that olefins are considerably more reactive than the paraffin, which can further lead to unwanted side and secondary reactions. Let's talk about the side reactions. Three types of side reaction can occur: hydrogenolysis, cracking, and isomerization. In hydrogenolysis, the addition of hydrogen into CC bond within a paraffin result in the formation of two small alkanes. Because hydrogen atoms and CH species are required for alkane hydrogenolysis to occur, this reaction is catalyzed by platinum side. Cracking also results in cleavage of paraffin to form two small hydrocarbons without hydrogen, but thermocracking hardly occurs at hydrogenation reaction conditions. Catalytic cracking is requires a catalyst with Bronsted and Lewis acidity. Fortunately, these side reactions are catalyzed by specific sites that are not required for dehydrogenation, which mean that high olefin yield can be obtained by careful catalyst design. Let's talk about dehydrogenation catalysts. Two main types of formulation are typically used for non-oxidative dehydrogenation of light olefins: noble metal-based and metal oxide-based catalyst. Platinum represents the metal that has been extensively studied, and various metal oxides have been successfully tested, but chromium oxide being the most used example due to its industrial use. Furthermore, promising results have been obtained using gallium, indium, vanadium, zinc, and molybdenum oxides. Tin-based catalyst. Despite the fact that platinum-based catalysts display very high activity in dehydrogenation reaction, their intrinsic selectivity to alkanes and catalyst stability are not entirely satisfactory. The addition of promoters which are able to modify the catalyst property of platinum is necessary to obtain an optimal catalyst. Tin is by far the most studied promoter. Tin suppresses hydrogenolysis and isomerization reaction, minimize the metal sintering, neutralize the acidity of the support, and facilitates the diffusion of coke species from the metal surface to the support. Also, these beneficial effects of tin promoter are well known and have been described in literature, as a working principle of platinum-tin system are still under debate. Indeed, both geometrical and electronic effects have been invoked to explain the mechanism through which tin influences the catalyst property of platinum. In any case, it is clear that tin oxide species present and the catalyst are reduced by hydrocarbon feed during the dehydrogenation reaction and during the pre-reduction step, yielding a platinum-tin alloy. the reducibility of tin oxide depends largely on the interaction with support. Strong interaction makes the reduction more difficult. However, platinum is closed assist with the reduction of tin oxide. From the geometrical point of view, it can be suggested that isomerization, hydrogenolysis, and the formation of coke precursor can all be suppressed by reducing the size of platinum nanoparticles. From the geometrical point of view, it has been suggested that isomerization, hydrogenolysis, and the formation of coke precursor can all be suppressed by reducing the size of platinum nanoparticles. The formation of platinum tin alloy and the partial covering of the platinum particles by tin species resulting in creation of small platinum assembles. Tin can selectively cover low coordination platinum sites such as steps, corner edge, and defects, which they believe are responsible for the hydrogenolysis reaction. The so-called ensemble effect can be employed to explain the geometrical advantage of tin addition to platinum-based catalyst. Dehydrogenation is to be structure insensitive reaction, meaning that a very small group or even single platinum atoms can catalyze the reaction. On the other hand, side reactions such as coking and are structure sensitive and require relatively large ensembles of platinum. A secondary effect of tin addition is the modification of electronic property of platinum. Alloyed metallic tin or tin 2+ species with close contact with platinum are able to transfer electrons to the 5d band of platinum atoms, which alters the adsorptive and catalytic property of the metal. Let's compare ethane dehydrogenation of platinum and platinum tin catalyst. The figure left side shows the conversion of ethane to ethylene and the selectivity of ethylene for platinum and platinum tin catalyst supported on magnesium alumina support as a function of time. Both catalysts exhibited a rapid loss in conversion during the first 40 minutes of time upstream, but then attained the period nearly constant conversion. As a main result, is clear that activity of platinum tin catalyst was in factor 3 higher than that for monometallic platinum catalyst under identical condition. And for selectivity for both samples reach close to 100%. Central and right figures show effect of addition hydrogen to the feed. For both catalysts, the production of ethane passed through a maximum and then a decrease with increasing H2 to C2H6 ratio. Addition of hydrogen also prevent carbon formation, at least decrease carbon formation. Do you have an idea why? Atomic steps, kicks, and sites with specific coordination properties can selectively break different bonds, CH, HH, CC bond, and etc. The catalyst performance of different size platinum catalyst is plotted in next slide. The smaller size platinum cluster have higher turnover frequencies, lower selectivity for propylene, and higher deactivation rate. The initial turnover frequency selectivity of propylene yield of different size platinum cluster are plotted versus platinum cluster. A catalyst with a smaller platinum cluster around 1 nanometer is the most reactive for propane conversion. However, the selectivity for propylene is lowest, around 50%, and the main product are CC bond scission products like methane, ethylene, and ethane. As the platinum cluster size increase, the activity of propane conversion decrease and the selectivity for propylene rise. The dehydrogenation reaction can be studied for almost a century, but the exact mechanism is still a topic under debate, particularly because the reaction is catalyzed by different material as a noble metals and transient metal oxide. The so-called Haruti-Polanyi mechanism, which was proposed in 1934, is most commonly used to describe a catalytic dehydrogenation reaction. This mechanism follows Langmuir-Hesselwood kinetics, where all of the surface sides of the catalyst are considered to be identical. The Haruti-Polanyi mechanism consists of four main steps: dissociative adsorption of the paraffin, CH cleavage of a second hydrogen atom, formation of hydrogen molecules, and subsequent desorption of both the hydrogen and the olefin, as shown on a scheme. Both CH cleavage step and dissociative adsorption of the paraffin have been suggested as a rate-limiting step of the dehydrogenation reaction. All dehydrogenation catalysts deactivated with time of strain, several processes being responsible for the activation of the different type of catalysts discussed in our previous lectures. However, there has been a clear consensus in literature since 1970s identifying coke deposition as a main cause of deactivation. The process of coke formation is very complex and not very well understood. In a scheme, several pathways for the formation of the first aromatic ring structure from propylene and similar molecules are proposed, which include cracking, deep dehydrogenation, and polymerization reactions. The formation of graphene layers on magnesium support platinum nanoparticles was studied by both in situ and ex situ high-resolution transmission electron microscopy. The image of high-resolution TEM indicates that graphene sheets grow from steps in the surface of platinum nanoparticles. The subsequent morphology of the graphene sheets is strong function of platinum particle size. For particles less than 6 nanometer in diameter, the graphene sheets form nanotubes or move from the surface of platinum nanoparticles and accumulate on magnesium oxide support. Complete particles enveloped by multiple graphene layers was only observed for particles greater than 6 nanometer in diameter. As a conclusion, I'd like to say that the current process build with employ chromium or supported on alumina or platinum tin supported on alumina catalyst. This catalyst and the technology have been advanced to point where the reaction can be run continuously for several years. Nevertheless, current dehydrogenation technologies still offer room for improvement, and though further advances are needed to lower noble metal loading, increase catalyst stability, and improve the energy efficiency of dehydrogenation process. Moreover, steps will need to be taken to overcome the reaction biggest drawback, that it is limited equilibrium conversion and preventing the site reaction at high temperature. Also, alternative catalysts, most notable metal oxides such as gallium oxide, molybdenum oxide, or vanadium oxide, have recent significant attention over the last decades are practically alternative to the platinum tin and chromium system has not yet been developed. Indeed, this alternative formulation deactivated too fast, mainly due to coke deposition and to the fact that their activity cannot be fully recovered by a regeneration step. Thus, further research will also be necessary to address those issues.